Welcome to day 15 of the 2024 Advent of Code. We have robots again today, and we have something about lanternfish that have food stored in certain locations in an elaborate warehouse complex. There is a robot that is moving around, pushing around their boxes with no regard for the lanternfish logistics or inventory management. And the lanternfish aren't brave enough to swim up to the robot, but if we can anticipate the robots, maybe we can find a safe option. So we have a map of the warehouse and the movements that the robot will attempt. And as the robot moves around the grid, it will push the boxes around. And if it would run into a wall or cause a box to move into a wall, then nothing moves, including the robot. So for example, this is a room with a wall in the middle, a bunch of boxes, and the robot here, and the robot will attempt to move in these directions. If the action causes it to move into wall, it doesn't move. And so here's a small example. Robot starts here. The first move attempts to move it left, which would put it into a wall so it doesn't move. Then it attempts to move up twice, but since there's a wall, it only moves up once. And then it moves right, pushing this box to the right by 1. And then moves right again, pushing those boxes over. It tries to move right again, but since it's all blocked by a wall, nothing moves. And then it moves down, shoving all of these 4 boxes into the wall. The next down move fails, etc. So on and so forth until we get to this state here. This is the final state for the larger example, and we want to figure out where all of these food boxes are. We use a custom goods positioning system to determine the locations, and the coordinate of a box in this system is equal to 100 times its distance from the top plus 100 times, plus just its distance from the left. And this doesn't stop at wall tiles, it measures all the way to the edges. So basically it is the 100 times the row coordinate plus the column coordinate in 0 indexing, because this would be 0, and as shown in the example, this is row 1. So for example, this here is in row 1, column 4, using 0 indexing, making its GPS coordinate 104. Finally, we want to sum all of the box's GPS coordinates to get our answer. So we have our input in 2 sections. The first is a bunch of lines representing the grid, and the second is a bunch of lines representing the movements. So we're going to have a top section and a bottom section, which are separated by 2 new lines. The grid is going to be the top section, and the moves are going to be the bottom section, but we don't want the new lines, so we can just split the lines and then join it on white space, or alternatively we could do bottom dot replace \n with space, but I prefer using this because it avoids issues with if the line breaks are not \n. Now granted, I did rely on them being \n here, so maybe that doesn't matter too much. So now we have the grid and the moves. I forgot to split the top on lines as well. Okay, so the grid here is a list of lists representing our grids, and the moves is now a single string without the new lines. So now we want to find the position of the robot. So we can search for it like so. And so now R and C represent the position of the robot. Again, in Python, the scope of a variable does not disconnect when the loop ends. And so when the loop breaks here, we also need to remember to skip. I have mentioned this in a past video before, but you can find my YouTube short called something about to do the Python else block to figure out what this means. And this gives us the position of our robot. So it was at row 4, column 4. So now we go through each of the moves. We want to get the move from a character to a direction. So the direction in terms of the row is going to be -1 for up, 1 if the move is down, and otherwise it'll be 0. We could also write this as this. This basically says if move is a key in this map, we return the value, otherwise we return 0. And then same thing goes for the column. So now we have the direction in row and column difference for our move. And so now what we need to do is we need to grab a list of all coordinates that are going to be moving. So we can call those targets. Basically, these are the targeted items for movement. Initially, that is the current row and column position of the robot. Now we need to find all of the boxes that it's pushing. So we can say while true, let's call TR and TC our current target coordinates, or let's just stick with the naming convention of current row and current column. We'll do CR plus equals DR and CC plus equals DC, moving over the current looking position over by 1. So for example, here we would move the target position from the @ sign to this box here. And now we have a couple of cases. So note that this is never going to be outside of the bounds of the grid because the grid is always surrounded by a box of walls. This is very convenient because it means that we just need to check if we've hit a wall coordinate. We do not need to check for the bounds of the grid. So if grid CR, or let's call this car equals grid CR CC. If it's a wall, then we set the go value to false and break. This will basically tell us if the robot is able to move. If the character is equal to an O, then we add it to the target list. Because there's a box and we need to move the box as well. And then we will continue searching from the new position and go to the next one to see what's behind that box. And if the character is a dot, that means that we've reached empty space, which means that we can proceed and we do not need to look further. So we just break, but go remains as true. These are the only 3 possibilities. We'll never get the @ sign because the @ sign was already here and we're not looking there ever. So now we have 2 states. Either go is true, which means that we have found all of the things that need to move and there's nothing blocking it, or go is false, meaning we ran into a wall. So if go is false, then we skip this move and just go on to the next attempt. Otherwise, we need to move all of our targets. So we need to modify the grid in 3 ways. First, the robot has moved, which means that it vacates its own position. So its position now becomes an empty dot. The second thing that happens is that the robot has now moved over by 1, which means that grid R plus DR C plus DC is equal to @ sign because the robot has moved in that direction by 1 space. And finally, all of the boxes move over by 1. So for all of the remaining targets, we can call it box row and box column in targets, except the first one, because the first one is the robot. Grid BR plus DR BC plus DC equals O, basically meaning that each of the boxes has moved over by that position. Finally, we just need to update the robot's position itself. And so we just do R plus equals DR and C plus equals DC to update the robot's position to the new one. Let's see what we have now. This is what we get, which is an exact match to what we expected to see. And so now we just need to output our answer. So the total is going to be the sum of the GPS coordinates and each GPS coordinate should only be counted if we have a box at that position. And the GPS coordinate is 100 times the distance from the top plus the distance from the left, which is respectively the row and the column. And so that'll give us our answer for part 1. I'd like to take a moment to introduce my sponsor, CodeCrafters. Many people ask me how I learned to code, and I've always learned best by actually going in hands-on with a project or problem rather than reading documentation or tutorials. That's why I love CodeCrafters, a platform that lets you build real-world software to both develop your problem-solving skills and train you in a specific language of your choosing. CodeCrafters lets you choose something to build, such as a BitTorrent or Git clone, and a language from a growing selection of over 20 languages and counting. You simply clone a repository from them, write your code to build your project with their intuitive step-by-step process, and push to get immediate feedback. I've been meaning to learn Rust for a long time, and when I get the time, CodeCrafters will be my choice for how I go from no experience to someone ready to start building my own things in Rust. Whether you're a beginner or already experienced in a language, CodeCrafters is a great way to start coding, pick up a new language, or master your language with its selection of projects. Doing a project teaches you more than just coding, as you can learn about protocols and existing software such as TCP, Kafka protocols, the inner workings of SQL databases, and more. If you sign up for free via my link in the description, you'll get 40% off if you choose to upgrade, which unlocks more content, gives you priority on test runs, grants access to perks which can save you money on all sorts of other platforms, and more. Plus, if you sign up within this December, you'll get access to all of the problems for free for 1 week. If you work at a company with learning and development benefits, be sure to check if CodeCrafters would qualify, so you don't even need to pay for it yourself. Thank you for your support, and let's get on with the rest of the video. For part 2, we have determined that reports indicate that a second warehouse also has a malfunctioning robot. This layout is very similar to the one we just solved, except the robot is twice as wide, and so to get the wider warehouses map, we start with the original map, but for each tile we make the following changes. Each wall becomes 2 walls, each box becomes a box that is twice as wide, each blank becomes 2 blanks, and the robot is now on the left half of its expanded coordinate. I think this means to say the warehouse is twice as wide because the robot is actually the only thing here that's not twice as wide, and the list of the movements does not change. This will give us a new map which is twice as wide with wide boxes. Funnily enough, it says the robot is twice as wide here, but it actually directly says the robot doesn't change size 2 paragraphs down. So let's make this alteration first. We're going to do this. So let's make a dictionary to represent the expansion. A pound becomes 2 boxes, or 2 walls. An O becomes a wide box. A dot becomes 2 blanks. And the robot ends up on the left half of its 2x1. And now we can say for each character in the line, we will replace it with its expanded form. This will give us a list of pairs, and we want this as a single list of characters. So what we can instead do is we can join this into a single string and then convert it to a list again. So basically what we have now is the grid, but twice as wide, and we still have it as a list of lists of individual characters. So now we need to replace a bit of our logic. This remains fine. We need to find the row and column position of our robot. What does need to change is our targeting algorithm, because now we need to keep track of multiple coordinates at once. Previously, we just need to keep stepping over one by one in a line until we reached a blank or a wall. But now we also potentially need to branch out, because as demonstrated in the example, the robot may now be able to push more than one box horizontally, because if the boxes end up like so, then this box, because it is halfway between these 2 boxes, will push both of them forward, meaning that we can now push a triangle of boxes. The way we're going to do this is basically like so. We start off with the robot and its direction. We see what is in front of it and add it to the set of things that needs to be tracked. If it's the left or right half of a box, we will add the other half of the box also to the set of things that needs to be tracked. This logic is not that complex because the box will always stay together. We can't break boxes in half because if the box gets blocked, then this movement is cancelled. We don't like shear the box in half. And once we have both of these, now we just need to look forward from both of these and say if we find something like this, then we also need to add the other half to the tracking list and so on and so forth. And then we only move once all of the positions have been confirmed to be unblocked, in which case we pick up all of these and move them forward by one. So let's do that like so. Targets is going to be an array. In this case, I've made the determination that because the input is so small, as you can see, it's a relatively small grid, we don't really need to be too concerned about lists becoming slow. So what I'm going to do is I'm going to iterate through the targets. So for crcc in targets, and here's a neat thing that Python allows you to do. So let's make a list with just one, and then we can do for x in a, if x is less than or equal to 10, a dot append x plus 1. So what do you think this will output? You might expect a to become the list 1, 2, but it actually ends up containing all numbers up to 11. And the reason for that is because you can append to a list as you iterate through it, and Python will not care, it will just go through the new elements as well. Note that this doesn't work in some other languages, like in Java, if you try to add stuff into an array list while you're iterating through it, it will throw you a concurrent modification exception, because this behavior can often be like unintentional. But Python doesn't give you this guardrail. If you want to do this, Python will allow you to. If you accidentally messed up and now have an infinite loop, Python will not save you. So let's proceed with the implementation here. So nr, we'll call that the next row and the next column. So nr and nc are the coordinates of the next item that's going to be pushed by this item. We have a couple of situations. If we run into a box, or sorry, if we run into a wall, then again we set go to false and break. This remains the same. If we run into the left half of the box, we now also need to add the other half of the box, which is to its right. And likewise, we also might need to add the left half of a box, which looks like this. The only caveat is that if we see a dot, we can no longer break, because just because one thing is not blocked doesn't mean everything is unblocked. For example, here, if this dot were replaced with a wall, then even though these dots are unblocked, this one is not, meaning that we cannot make this movement at all. So we cannot take an early exit on dots. So we delete that part and we don't need to put anything else there. This will keep looping until we have found all of the targets. Now, one thing we do want to be careful of is that we might end up adding targets multiple times. So if we've already looked at nrnc, then we don't need to add it again. This can happen, for example, if we, let me see, is this something that can happen? If we have a situation like this, for example, pushing up would add this, which would add this and this, and then, or rather it would add this directly. And then when we push this up, we'll add this, which also adds this directly. And then when we push up, we'd add this again. So yes, it can happen where we'll add a target twice. So we want to avoid doing that. So the reason I am not making target a set here is because the iteration through sets does not work the same way, where if you add stuff in, I think you can encounter issues. I'm actually curious if that is the case. Yeah, sets don't allow you to change their size while you're iterating because sets aren't ordered, so it would cause issues. unlike with lists. So that's why I'm not making this a set. But at the very least, even if we add multiple targets, it's not much of a big issue. We just want to avoid double checking again, because then that could blow up exponentially. For example, if we check this twice, then we add this twice. And if we do that again, this one would get added 4 times. And so that could blow up exponentially. We can be fine with adding targets twice, we just don't want to check them twice. So if nrnc is already in the targets list, that means that we don't need to check it again because we've already checked it when we added it. So likewise, if we run into a wall, we still exit. And this logic also needs to change a bit. Previously, I made a couple of assumptions. This assumption can remain, which is that the robot leaves a blank in its place. This assumption can stay where the robot moves forward into its new spot. But this part does need to be updated because we now have a bunch of other targets and they could either be the left or the right half of a wall. So we'll do a couple of things. First of all, this is the robot, which is the first item in targets. So we still want to skip it. For each box in the targets, we want to vacate its space. Now, something else might get pushed into it, but for now, let's vacate it. Then we want to push each box into its new location. So what we can do here is for BRBC in targets 1, just like we push the robot into its next spot, we can push each box into its next spot. Except normally we'd like to do something like this, but grid is already being modified in real time, so this would not work. And so instead we can just create a copy of the grid. This will create a shallow copy because for each row in the grid we call list, and if you call list on a list, it'll create a new one that doesn't reference the same thing. Just as a demonstration, if we have a list A and we have B pointing directly to the same reference as A, then any modifications to A will also impact B. But when you call the list function, it constructs a new list by taking each element from A, which means that if we now update A, B does not get updated because it's no longer a reference to the same underlying object. And the reason we are doing list row for row and grid and not just list grid is because if A is a list of lists, then what this means is that B is not a reference to A. However, what we've done is we've taken each element of A and put it into a new list, but that means that these lists are still the same underlying objects as these, just that they're contained in a different surrounding list. And what that means is if we do this, then that would influence B. And so in order to make B completely decoupled, we would have to use this trick for each row. And so now A and B are different lists, and the contents of A and B are also different lists. If your list gets even deeper, you would need to do this recursively, and so once it gets deep enough, it makes more sense to just like import the deep copy function, which basically just creates a copy of the object that doesn't have the same reference. So this would make more sense if you had a larger grid, or a larger structure, but because this is just a grid, it's perfectly fine to just do this. I think I'm actually just gonna import deep copy because it's just cleaner to do it this way. Okay, so the clone of the grid, the copy, is going to be deep copy of the original grid, which means that these modifications no longer alter the copy, and so we can just grab the old items from the copy. Basically what this is saying is for each of the targets except the first one, which is the robot itself, the item that was previously at that coordinate ends up in the new position moved by the distance of the robot move. And each of the previous locations that doesn't get overwritten by a box being pushed into it ends up vacant. The robot ends up in its new position, and the robot's old position ends up vacant. Finally, let's see how we score this. The sum of the GPS coordinates, in this case, the GPS coordinates are measured to the closest edge of the box in question. So the top edge is still the same because the boxes only occupy one row, so this remains the same. And the closest edge to the left is the left one, basically meaning we are just looking for the coordinate of each opening square bracket. This is not supposed to take long to run. I do wonder which step is taking so long. It doesn't seem to be taking long on each individual move. I skipped ahead a bit. It seems like it might just be a bit slow. So I believe I forgot to remove the print statement. I believe this gives us our answer for part 2. It just takes a bit of time to run. I think the issue here might just be that I overestimated the efficiency of this solution. Let's see if this at the very least changes this a bit, so we don't try to do duplicate operations. Still doesn't seem to be improving it. I wonder if deep copy is slow, because that's not what I was using earlier. Okay, yeah, deep copy is just slow apparently, so I guess that's a good reason not to use deep copy then. It makes sense because deep copy doesn't know the structure of our list in advance, so it has to figure out the structure by inspecting it. So if we already know the structure, I guess it makes sense that it's faster to do it this way. In any case, that gives us our answer for part 2. So thank you for watching, I hope you enjoyed, and I'll see you again tomorrow.